day, everybody. Today, for this seminar, we have KORNIKAR Sen, who's a PhD student in the Harish Chandra Research Institute. She's a PhD student of Ujjwal Sen, no relations. And she's going to speak about some nice work she's done in the field of quantum batteries. So, KORNIKAR, there you go.
Hello everyone. Thank you for giving me the opportunity to present my work here, and thank you for the introduction. So I will talk about regional versus global operation in the context of quantum battery and state discrimination tasks. So this is the outline of my talk. I will first briefly discuss about global and local operations, then I will move on quantum batteries. I will mainly focus on energy extraction from quantum batteries, then I will discuss incompatible measurement and state discrimination tasks. So here I will discuss about state discrimination tasks using global operation, local operation and local operation plus classical communication. Then finally I will summarize. So let us start with global and local operations. Let us say there is someone and there is another person and they have faced some problem and they want to discuss about the problem. So they can discuss about that through phone calls or emails or Google Meet or Zoom or something. That would be a local discussion. Or they can meet face to face at some place and can discuss about the problem. So that will be a global discussion. So it is obvious that global operations are more powerful. I will also give some examples to prove this statement. But local operations are cheaper. In case of local operations, you do not have to move from one place to other, you do not have to carry your devices with you and so on. So here is an example. This is Alice and this is Bob and they have some systems. So by local operations you can only create these type of states. If you use local operation plus classical communication, you can create these type of states, but you cannot create entanglement through local operation. To create entanglement, you should depend on global operations. So this is an example. There is another example, say that Charlie has given a bipartite state to them and he has said that it is one of the Bell states. Now they cannot distinguish between these states by using local operations only. So to distinguish them, they must use global operation. But that does not mean that you can't do anything using local operation. If Charlie has specified that the state is one among any two of them, then they can distinguish between those two states through local operations only. So this is all about the brief discussion on global and local operations. So let us move to quantum batteries. So nowadays we want everything to be of smaller sizes so that it is easy to use and flexible to carry. Now when the size of the device is very small, the battery you are using inside the device should also be very small. Now in case of atomic size batteries, the quantum mechanical effect will affect the working performance of the batteries. So that is why it is important to know about quantum batteries. So quantum batteries are like a energy storage device. You can extract some energy from it to use the energy, or otherwise you can charge the battery also. So the battery is defined using a system. Initially say it is in a state rho 0 and its energy is defined by a Hamiltonian. So let us say at some time you switched on a field and then after some time say t, you switched off that field. So in between this time t, the battery state will evolve. So let us say it was the initial state, so it is the final state. So it is the initial state's energy and it is the final state's energy. And this is the energy gap. Now if W is greater than 0, you can say that you have successfully extracted energy from the battery through this unitary operation. Now the motive is to extract the maximum amount of energy from that battery. So you can use the optimal unitary. Now if you apply the optimal unitary on the state transforms to a passive state. So what is a passive state? The passive state is the state from which you cannot extract any more energy using unitary operations, because you already have extracted all of its energy. So passive states in general has some properties which obviously depends on the Hamiltonian. So it commutes with the Hamiltonian. Now if for a particular order of the eigenenergy states, if E1 is the lowest eigenvalue of the Hamiltonian and E2 is the second lowest, then for the corresponding order, the eigenvalue of the passive state should be the largest. So lambda 1 is the largest eigenvalue and lambda 2 is the second largest eigenvalue, and so on. So if Ei is greater than Ej, then lambda I should be less than lambda j. So from this first property, you can find the eigenvectors of the passive state. Now from the third property, it says that since that particular passive state which you are getting here is related with the initial state through unitary operation. You got this by applying unitary on rho 0, and unitary cannot change eigenvalues. So sigma will have, the passive state will have same eigenvalues as rho 0. So here from the third property you get the eigenvalues, and this second property tells about which eigenvectors goes with which eigenvalue. So from these three properties you can just write the passive state, that is the minimum eigenvalue goes with the eigenstate which has the maximum eigenenergy, and so on. So let us give some examples. So for PO state, the passive state is the ground state, because you can start with any state, you can operate unitary and you can always get the ground state, and the ground state has the minimum energy, so then you can't extract any more energy from the ground state. For 1 qubit mixed state, thermal states are only passive state. For in this case, corresponding to every passive state, you can define a temperature for which you will get the thermal state, and that thermal state will be exactly equal to the passive state. But if you go to higher dimensional mixed state, thermal state is still an example, but it is not the only example. So the results about the quantum batteries which I have discussed till now is taken from this paper. What we considered is a bipartite quantum battery. Now the battery has two parts. One part belongs to Alice and the other part belongs to Bob. Now we consider that the two Alice and Bob are situated in two different locations, so the two parts doesn't interact with each other. So we have taken local Hamiltonian. Now in this case you have two options. You can still extract energy using global operation, but in that case you will get the same thing as I discussed. So the second option is you can now extract energy through local operation, like these type of unitaries. Alice operates unitary on her part and Bob individually operates unitary on his part. So this is Alice unitary, this is Bob's unitary, so this is the total unitary. Now again we can optimize over these local unitaries. So if you then operate the optimal unitary, what you get is the locally passive state. That state from which you cannot extract any energy through local operation. You can of course get more energy using global ones, but you can't extract any through local operations. So we have defined locally passive state and we have found some properties of the local passive state. Again the passive state will depend on the Hamiltonian. So in this case the subsystem of the passive state will commute with the local Hamiltonians HA and HB. So like if you trace out the Bob parts, then Alice's part will commute with Alice's Hamiltonian. Similarly, if you trace out Alice's part, then Bob's part will commute with Bob's Hamiltonian. Similarly, if the eigenvalues of Alice's Hamiltonian is in increasing order, then her part of the passive state's eigenvalues will be on the opposite order, that is in the decreasing order. Similarly for the Bob's case. Now let us focus on the energy extraction from quantum battery. By energy extraction, I will discuss about global extraction as well as local extraction. By global extraction, I mean this type of unitaries, and local extraction means this type of unitaries. So as I said, your battery has two parts, so you have two options. You can just operate local unitaries to extract its energy, but by local unitaries you won't get all of its energy. So to extract the remaining energy, you have to bring the batteries together and operate global unitaries so that you get the remaining amount of energy. Now consider 2-qubit battery. I say that you have a state which has a particular entanglement E and it is locally passive. When I give you these three conditions, you can only have one state of this kind. Now if you can't extract energy through local unitary operation, since those are locally passive states, so you operate the optimal global unitary and see how much energy you are getting. So that amount of energy will of course depend on the entanglement. So this is the expression. By entanglement, I always mean logarithmic negativity. So to plot this function, we have considered these values. These are just arbitrarily chosen. Now you see, with entanglement, the value increases. So the globally extractable work from the locally passive states increases with entanglement. Because in case of pure states, say when the states are separable, you can extract all of its energy through local operations only. So then after getting the locally passive state, when you apply global operation, you don't get any more energy from that state. So that's why it starts with 0. But when there is a finite amount of entanglement, that entanglement somehow restricts the state so that you can't get all of its energy by only using local unitaries. As I said, for pure states, there is only one locally passive state which has a particular entanglement E. But when you move to mixed states, you can get a set of locally passive states. So we have optimized over that set and we plotted with respect to entanglement E. The nature is still same, it increases with entanglement. But the interesting difference here is that in this case, even when it is separable but mixed, you get some energy. So it starts with 2, here it started with 0. So the
here you're optimizing the maximal global extractable work, or
yes,
you're maximizing it.
Yes.
Okay.
So this is like a upper bound that how maximum amount of energy you can get from a mixed state which has a particular entanglement E. So now let's move to a more general state, that is a pure state which may not be locally passive and it again has a fixed entanglement E. Now if you maximize the globally extractable work from that state, it has an opposite behavior, it decreases with entanglement. This is because when the state is separable, and now since we are maximizing over all such states, you will get this maximum value when the both part of that separable state are in excited state. So you apply unitary, you flip them to the ground state and you get the maximum amount of energy that way. But when say they are in a 0, 0 plus 1, 1 kind of state, so they are in a superposition of both being ground state and both being excited state. So because of the contribution of the ground states part, you can't get any energy from that part. So the total energy you are getting from that state is much less than the case when the states were separable. So again we have maximized here over the mixed states having entanglement E, and you can see from the behavior of the curve, actually the maximum value is being reached for pure states only. So this curve has actually the same nature as this one. but we have numerically optimized this so the curve doesn't look that much smooth.
How do you optimize with something in programming, I guess?
No, actually we have optimized using a package which is non-linear optimization.
Okay.
So these are constants on the logarithmic negativity. So these are not linear constant. So yeah.
Okay, sure. Yes, but a constraint on logarithmic negativity is also a constraint on the negativity. The negativity is actually an SDP value.
Yeah, yes, but yeah.
So I was wondering why there are so few points, right? I mean, I think you could really plot the whole thing.
Yeah, but we actually just considered point with 0.1 gap. We can fill those, but it's okay to just see the nature. Okay, so yeah, up to now I have focused on globally extractable energies. So I have discussed these two quantities. This is the maximum amount of global energy you get from a set of pure states, and this is the amount of global energy you get from locally passive states. Now here is a maximization over the states. Now consider that this maximization is reached for a particular state rho. That state rho will also have some locally extractable energy. So let us say LE bar is the amount of locally extractable energy from that state for which this maximization has been reached. So we have plotted here LE bar with respect to the entanglement with the red line. Now there is another quantity, that is maximum amount of locally extractable energy. So we have also found that and plotted those using these black points. Now you see the black points are all situated over the red line. So from here you can say that LE is actually equal to LE bar. So LE is the maximum amount of local energy, and LE bar is the local energy you get from the state for which global energy was maximum. So from here you can say that is the state for which global energy is maximum is same as the state for which local energy is maximum. Now the difference between this G and LE bar somehow gives the power of the global extraction, because G is the global extractable energy and LE bar is the local energy from that state only. So we have found the difference, and we saw that it's actually exactly equal to GEP, which is the maximum amount of global extractable work from locally passive state having that same entanglement E. So we can say that is the extra advantage of using global unitaries is equal to this energy. And here you see that the local energy and the global energy has similar behavior, but since GEP is given by the difference between these two curves, so GEP has the opposite behavior. So now we have these theorems that the difference between the maximum amount of global extractable energy and the locally extractable energy from the pure state that provide the global maximum is equal to the amount of maximal global energy available from the corresponding pure locally passive state. And by corresponding I mean that it has same entanglement. And the proposition which I discussed, that the pure state for which global energy is maximum also provides maximum local energy. I talked about only 2 qubit batteries, but it is also true for 2 cross D systems. Now let us consider Q-trit system. So here again I plot LE, the maximum local energy with the red line, and LE bar, the local energy for which global energy is maximum, which is this magenta line. You see there is a finite difference between this red line and the magenta line. So here you see that LE bar is not equal to LE. So the proposition here is not valid here. Now then in the qubit system you had the GE minus GEP was equal to LE bar. Here again we plot GE minus GEP for 3 cross 3 system, and see this is the green line, which is like a different line which is not overlapping with the magenta line or the red line. So, it is a completely different line. So, you see this is again not equal to LE bar or LE. So, in Q-trit system, these 3 quantities are exactly different from each other. So, the proposition or the theorem, none of them are valid here. So, we have considered a bipartite battery shared between Alice and Bob. They had some entanglement, and I have shown you some curves. Now, you may think if those curves can somehow be used to predict the entanglement shared between Alice and Bob. But it cannot exactly predict the exact value, but it at least can give a bound. So, let us say they share a battery. Now, they have extracted all of its locally available energy. So, and the amount of energy they got that way is L. So, this is LE curve, the maximum amount of local energy you get when the entanglement is E. This L is intersecting the curve here. E1 is the corresponding entanglement point. Then they can surely say that the entanglement must be less than E1, otherwise they could not have received that much of energy. So, they can say E is less equal to E1. Now, they have only used local unitaries. Local unitaries will not change entanglement. Now, they bring the 2 batteries together and 2 parts together and apply a global unitary. Now, since they have extracted all of its energy through local operation, the state is now locally passive. Now, they are using global unitaries to extract its remaining energy, but they now may not use the optimal one. So, let us say now the energy they are getting is G. This is the line which says the amount of energy you get when entanglement is E from locally passive state, and here the line intersects at E2 entanglement point. So, here again using the same logic you can say that the state must have entanglement greater than E2, otherwise you could not have get that much of energy. So, from the whole protocol you get the bound, that is E is greater than E2 but less than E1. So, up to now I have discussed ideal situation. The battery is isolated from the world, it is not talking with any system of the world. Now, let us move to a more realistic situation where we have considered this is the 2 qubits of the battery, they can be entangled. Now, 1 qubit of the battery is opened to an environment which contains spin half particles. Now, one particle comes, interacts for some amount of time and goes away, and a new particle comes. So, say it interacts for delta t amount of time, and the time in between 2 consecutive interaction is negligible. So, when you see this, after every delta t time when a new spin is coming, that spin does not know anything about the previous interactions. So, it does not have any memory. So, you can see it as a Markovian interaction. So, considering such situation, we have again plotted the global energy extraction. So, here n represents the number of time the qubit of the battery interacted with the spins of the bath. So, when n is equal to 0, it represents the noiseless case, and when you increase n, that is when you increase the number of its interaction, the global energy decreases. Here we have plotted the same quantity with respect to n. Here also you can see that it decreases with n. K's are the coupling strength between the environment and the battery. So, also you can see if you keep n constant and just increase the coupling, that will also decrease the energy of the battery. So
it is dependent on the model they use for the interaction, but I could imagine a model of interaction that replaces the state by a state of very high energy, right? I mean, in which case you would get more, right? I mean, it would be the opposite.
yeah, so we are considering the environment as a noise. Like we are considering a situation, say you charge your mobile 100%, you leave it somewhere and you come back after 2 years. It won't be still in 100%, it will lose some of its charge. So we are considering that case. But there are works where they like use environments having particles which has higher amount of energy, and they use those environment to charge the battery. So in that case the environment gives energy to the battery. So, but here we are considering that we don't have any control over the environment. It's just something which is interacting and absorbing
like
energy.
White noise or something.
Yeah, here we have considered a particular amount of interaction.
Yes.
And we considered the initial state as ground state. If we
What is the CP map that is implemented on the battery, on this part of the battery? I don't care about the interaction or the initial state. What is the CP map? What is the equation? What is the Lindblad equation?
Yeah, actually you can derive the Lindblad, but since it's a very small system, we didn't use Lindblad here. We have just operated unitary on this there is only 2 qubits, so you can operate unitary on them together. Then you trace out the spin.
And what is the CP map that is affecting the battery? What is after you trace out the environment?
It's a spin bath.
Tell me what is the map? What is the map? I don't care about how you implement the map.
No, actually that's what I'm trying to say, that we haven't actually derived the Krauss operators.
Okay,
that's what we can derive, but actually we didn't require it, so just we use the total unitary.
And what is the unitary?
That's like it has some sigma z type of its local Hamiltonian, and the interaction is sigma x plus sigma y sigma y. So to see the Krauss operator, I have to just trace out the paths from the unitary. That part I didn't do here. So okay. So as I was telling, so it's obvious that those spins are in ground state, so they are coming, interacting and taking some of the battery's energy. Now here I have plotted the graphs after each delta t time. So these are the amount of energy you get after each delta t time, and so these are just points, and I have joined those points with lines. So here these are points. We have also seen the nature of the other kind of energies, that is the locally extractable energy and global energy from locally passive states. All of them have similar behavior. All of them decreases with increase in n. Now I ask that if there can somehow be any non-Markovianity, and if that non-Markovianity can somehow improve the situation. So as I said that after each delta t time a new spin is coming, the interaction is obvious Markovian. We can't put any non-Markovianity there. So we look into inside the time duration. So the one spin is interacting with the qubit for delta t amount of time. Now if you increase the time duration, say you take a large time duration, in between that time this spin is getting changed, and this spin knows about its change. So this spin is getting some memory about its interaction. So if you increase this delta t amount, so the non-Markovianity can come for that one interaction. When the spin goes away, a new spin comes, that new spin doesn't know anything. So we have quantified that non-Markovianity, and that non-Markovianity of course depends on this time duration delta t. So, to quantify that non-Markovianity, we have used this property that say you have a green ball and a red ball, they are orthogonal. You put them inside two independent baths. These are same bath, but are separated. So, if it is a Markovian interaction, with time the information goes from the balls to the bath. So, with time the information fades away. So, initially they were orthogonal, so you can distinguish them perfectly, but after a time the distinguishability between them decreases because the evolution is Markovian. But if the evolution is non-Markovian, then there will be a particular time after which the environment will give back the information to the system. So, if you say that this rho 1 and rho 2 are the states and this is the distance, so for non-Markovian evolution, the time derivative is always less than 0, because for Markovian evolution, the distance always decreases, the information always goes away from the system. But if the evolution is non-Markovian, there will be some time after when this quantity becomes greater than 0. So, the quantification of non-Markovianity depends on this property. So, this is just maximization over the initial state and integration over this quantity over time, but you only take those times for which lambda is greater than 0. So, for Markovian evolution, lambda is never greater than 0, so you get 0, Qn is 0. This measure is taken from this paper. Now, we focus on our interaction. So, that is one spin is now interacting with one qubit for a large amount of time, and how the non-Markovianity depends on that amount of time delta t. So, you see for delta t small, the interaction is Markovian, but after a point non-Markovianity increases and it keeps on increasing with delta t. Here now we have plotted the global energy from the battery. Now we are plotting also in between those times. So, now if you say delta t is 0.4, that is from this Markovian region, here you start from here, the energy is decreasing with time. This is the 0.4 point, this is the time axis. So, here a new spin comes, again the energy decreases with time and it keeps on going decreasing its energy. But now let us take delta t is equal to 1.4 from the non-Markovian region. In that case, the energy at first decreases with time, but then it reaches a minimum value, after which the energy starts increasing. This is the 1.4 point, a new spin comes here. The moment the new spin comes, the energy again starts to decrease, but then here you see after reaching a minimum point, it again starts increasing. So, it is just goes on oscillating in this way. Now, if you increase delta t more, you will see that it is decreasing and then increasing, and even at the time of increasing it is reaching a maximum value, after which again it is decreasing. So, if you keep on like increasing delta t, you will see there is oscillatory behavior. So, there are a moments when the environments are only absorbing energy, and then there are time intervals when the environment is releasing its energy to back to the battery. So, when the environment is only absorbing energy, you are getting these flat regions, and when the environment is giving back its energy, you get this increase in the curve. So, we couldn't find any one-to-one relation. So, like if the non-Markovianity is say 0.3, then what will be the corresponding energy? But you can see these graphical nature of the globally extractable work just mimics the non-Markovianity in the system. Okay, so this is the take home message. Having closed battery is the best. In case of closed battery, the energy remains constant with time. But if there is interaction, then non-Markovianity is more beneficial, because in case of Markovian interaction, the battery only loses its energy, and in case of non-Markovianity, there is some chance of getting back the energy from the environment. That's all I wanted to say about quantum batteries. So now let's move to incompatible measurements and state discrimination tasks. So let's say mx is a set of measurement which can be measured simultaneously using a parent measurement g. Then it is called that the set is compatible. Mathematically you can write it in this form, where g lambda is the output operators of g and a given x are the output operators of mx. So from here you see, from the statistics of g lambda you can get the measurement statistics of m a given x. Now if a set of measurements is not compatible, then we say that it is incompatible, and you can also measure this incompatibility. So this is a robustness kind of measure. The minimum amount of noise you have to add with the measurement so that the whole thing becomes compatible. So now you can write the whole thing.
What is the noise? Is it another POVM?
Yeah. So that's what. Yes. So by noise I mean another set of measurements you are joining with this so that the whole thing becomes compatible, so that it has some obvious properties, it's greater than 0 and complete and so on. So as first you may think that okay, then obviously compatible measurements are more powerful since you can apply them simultaneously. You may not like incompatible measurements, but there has been shown that there exists some state discrimination tasks where incompatible measurements have some advantage over the compatible ones. So I will discuss one example of a state discrimination tasks. So there is a girl, there is a boy, and it's the boy's birthday, and the girl is confused about what to gift him. So she directly asks the boy, and the boy says, okay, you can give me a t-shirt, a watch, or maybe a pair of shoes. So the girl chooses 3 t-shirts, 3 watches and 3 shoes, but she is still confused among them. So then she randomly chooses a set, an ensemble, and from that ensemble she randomly chooses a gift and gives that to the boy. Now the boy wants to know which gift he has received. Classically it's simple, you just open the wrapping paper and you see, but quantum mechanically that may not be so trivial. So the boy has some measurements using which he wants to know about the gift. So there are 2 situations. The girl can tell about the ensemble before the measurement, that is if it is a shirt or a watch, she can tell it before the measurement, or she can tell about the ensemble after the measurement. So here the boy decides about the measurement depending on the ensemble's information. Here he can't decide the measurement, but at least after looking the output he can guess the gift by depending on the information of the ensemble. So it has been shown that there you can define 3 types of probabilities. That this is the probability of guessing when the boy doesn't know about the ensemble at any point of time. This is the probability when the boy knows but after the measurement. So it's the post measurement information, and this is the probability of guessing when the boy knows before doing the measurement. So the probabilities will obviously satisfy this relation. It has been shown that these probabilities are equal if and only if there exist compatible optimal measurements for all Alice's states ensembles. So in this paper they have shown that for a pair of measurements, if you have seen that the probability of guessing when you have the information prior to the measurement is greater than the probability of guessing when you have the information after the measurement, then you can surely say that A and B are incompatible, because if you have used compatibility, these should be equal. So, there is another paper in this line, we mainly focused on this result. So, there is two probabilities. This is the probability of guessing when you have this set of ensembles, and this is the set of measurements, and you have the information before doing the measurement. This is the probability when you have the information after the measurement, but you have maximized it over all possible compatible measurements. So, this ratio is upper bounded by 1 plus IR. So, what is IR? IR is the robustness of incompatibility of this measurement MX, set of measurements. So, also they have shown that corresponding to every set of measurements, there exists an ensemble for which this equality can be reached.
So, if for example, two measurements, you have two measurements which are compatible and exact.
Consider a very simple example. You have two measurements that are exact measurement and commute with each other, so they are compatible with each other. Then the guessing probability will be 1, right? Will be perfect.
Depends on the state you want to distinguish.
Depend on the state.
Yeah.
But you will be a maximal guessing probability, right? If they are exact.
What do you mean by exact? It's
exact, I mean they commute with each other.
okay.
Two measurement commute with each other.
Yeah. Okay.
Because not all, because there could be compatible measurement,
Mm-hmm.
but they don't commute with each other. But if they commute with each other, then it seems to me that the guessing probability would be even higher. And then I just guessed that it would be guessing probability.
No,
I mean the upper bound. You get the upper bound.
no, I don't
This is just an
think
example.
so. It depends on the set of states. Of
Okay.
course. So.
Okay. But it should also depend on the
So like,
statistics of the measurement.
So, may I use that board? So, say,
Or I don't know, for the statistics in YouTube. Is in YouTube is only this, or is there a, I don't know.
I would check. Just start writing and then we can move it.
Here, we don't. We have to know whether we have to put the data.
okay, I just say like you have a 0, 1 state or plus minus state. So, there is an ensemble having 0, 1 state and there is another ensemble plus minus state. And Alice is saying that I have chosen the gift from the 0, 1 state. Now, you can obviously do the sigma z measurement to distinguish. And on the other hand, when Alice says I have chosen the state from the plus minus state, he will do sigma x measurement and he can perfectly distinguish. But if you choose like sigma x and sigma x square kind of measurement, you couldn't have distinguished between them. So, that is why here you are getting an incompatible advantage. Okay. So, yeah, so, yes, so this is,
You're saying that the inequality is saturated for some.
yes, yes. They have proven it. So, and since this is a positive number and so the whole thing is greater than 1. So, when you are getting that saturated value, this probability is of course greater than this one. So, in those cases you are getting an advantage from that incompatibility. So now we have considered a more complicated situation. So not complicated in the sense of science, but in sense of relationship. So now the girl has two boyfriends. The boyfriends are friends with each other. So now the girl chooses a bipartite gift and gives one to boy 1 and the other to boy 2. Now these two boys lives in two distant locations, so to know about the gift, they can only use LO or LOCC operation. So local operation and local operation plus classical communication. Now considering these two situations, so these are the probabilities using local operation set of ensemble, and this is the measurement that boy 1 has, and this is the measurement corresponding to boy 2's lab. And this is the probability when you have the information before the measurement, and this is the probability when you have optimized over all compatible measurements. So this whole thing is less equal to 1 plus Im into 1 plus In, where Im and In are the incompatibilities of M and N. Even if you use LOCC operation, you will get the same upper bound. And in both cases, we have here also we could have proved that corresponding to every pair of set of measurements, you can define a set of ensemble for which you can reach these inequalities. So these becomes equal. Now you can think of this situation as a global situation, that is the boy 1 and boy 2 are together operating this measurement. So here you had a global bound, 1 plus IR will be now the incompatibility of M cross N. So let us say it is 1 plus I M cross N. We have seen that this 1 plus I M cross N becomes equal to the RHS of these inequalities, which is 1 plus Im into 1 plus In. And all of these cases, the global or local or LOCC, has an example for which these inequalities can be reached. So if you consider that optimal set of ensembles for which these becomes equal, for that optimal set, this ratio is equal to 1 plus I m cross n, which is equal to 1 plus I m into 1 plus I n, and these are also equal to 1 plus I m into 1 plus I n. So in that case, you are not getting any non-locality. So we say that no non-locality is present in that optimal ensemble task. But I of course want to emphasize here that no non-locality is present in the ratios, but the individual probabilities may have some non-locality, but when we are taking the ratios, the extra terms are getting cancelled out. So this all. So in conclusion, I want to say that global operations are more powerful, but local ones are cheaper. Passive states for quantum battery form an important concept. We defined and tried to characterize locally passive states. We observed the behavior of the battery in presence of noise, and we saw that non-Markovianity can help. Incompatibility of quantum measurements known to be connected to quantum state discrimination. We made the same connection for local measurements, and here we have considered LO as well as LOCC operation. But I want to emphasize by LOCC operation, I mean only one-way LOCC operation. So these are the papers which I have discussed. Thank you.
Thanks, Kornikar, for this very nice talk. So, does anybody have questions? So in the example, but I still didn't get very well, right? I mean, so can you show the formulas for the set estimation, the ones that related the robustness? Yeah.
Or the formula for the robustness.
That's fine.
Okay.
So in this case, each part is making a measurement and then they communicate the result to each other at some point or something like that, right?
Mm-hmm.
Okay.
So Here they communicate and here they don't communicate. So this is only LO, this is LOCC.
No, what? They must communicate at some point, right?
Oh yeah, after doing the measurement they
Yeah,
communicate.
exactly.
Yes, sorry,
Okay.
yes.
So, sorry, what is the, okay, the epsilon is the set of states. Is that the
Set of ensemble,
ensembles, okay.
the ensembles has a set of states.
And what is below, right? And below is maybe the optimal probability or what?
Yes,
Yeah.
optimized overall compatible measurements.
All compatible measurements.
Hmm.
Okay.
So that's why when it's greater than 1 you see there is
compatible and local.
compatible and local.
Okay, good, thanks. Okay, I understand.
Okay.
Good. No more questions?
So you said global operations are more powerful for extracting energy from the batteries, right? And evacuate the battery even more than local operations. But could you, for example, but if you add entanglement into the batteries, then you can get the same thing with the local operation as for global operation, right?
No, it's opposite. When there is no entanglement, then the global operation is equal to the local one. So if, yeah, because of that correlation you can't just being to a distant parties you can get the work energy.
Sorry, also when the state is not pure?
Yes,
Okay,
yeah, when it's pure.
Oh, when
Yeah.
it's pure, okay.
When it's mixed, even if it's separable, you can't get all of its energy through local operation.
Oh, okay.
So, 1 minute. So this is the energy you get after doing local operation, then you are doing global operation. So this is when it's mixed, you are still getting 2 unit of energy. But when it's pure, you won't get anything.
But this in the cubic case, you have higher dimensions, is it the same or?
Yeah, like we have gone for mixed state, we have gone through 2 cross 3, it's same, and we are kind of convinced with the result because it's like the classical mixture is somehow restricting the energy. So for higher dimension also the same thing will appear. It's my like intuitive guess.
Okay.
But we have checked up to 2 cross 3 system for mixed states.
Okay. Good. So thank you very much.